I don't see that on my screen. You're only the ones who's seeing it. So if something is going wrong, let me know. If something is out of range. Okay. All right. So we started with Ohm's law. V equal to IR, and we said V and I have a directionality. You have a resistance R, plus minus is the voltage drop V, and this direction is current I. Okay, so let's start with a problem which we did in the quiz. Say R1 and R2. And I said the voltage at this point was V plus 5, the voltage at this point was V, and I'm asking you what is the voltage drop across R2 plus minus in this direction. Right, so answers.
We know the voltage drop across the two of them is 5.
Okay.
And so then you could do a voltage divider.
Okay.
Somehow.
So what would that be?
5 times. If you're going for R2, then it would be 5 times R2 over
Okay.
R1 plus R2.
All right. So okay, what Lindsay is saying is the voltage drop across these two resistances is 5, right? That's V plus 5 minus V. That's 5. Okay. And that means since the voltage drops proportionally across these resistances, right? Let me do that step by step so that you'll see how we derive the voltage divider rule. Okay. So the whole drop, let's say the current I is going through R1 and R2. So I know I is equal to V plus 5 minus V divided by R1 plus R2. Right. So that will be equal to 5 divided by R1 plus R2. Okay, so that's volts. And then the voltage drop, so this is current I in this going through this resistance also. So the voltage drop from left to right would be that current times R2. So VR2 will be equal to 5 volts times R2 divided by R1 plus R2. Okay, so that's how we derive the voltage divider rule. Okay, if there are two resistances in series, which is important, if they're not in series, you cannot apply this rule. They have to be in series. That means the current going through them has to be the same, right? And one of their end terminals should be the same, and the other should be different. So that's when they are in series. Okay, and if that is the case, then you can take the entire voltage drop across both the resistances and divide it proportionally amongst them, right? And another things you can also, whenever you come with an answer, you can also do some sanity checks, right? What are the units here, right? So this 5 volts has units of volts, and in this, the numerator and the denominator are both resistances, so this is unitless. So the right hand side is volts, which makes sense because it has to be volts. Okay, so that's Ohm's law. Any questions so far? Okay, so now let's talk about Kickoffs voltage law. Okay, all right, can anybody remind me what that law is?
You take a certain loop and you add all the voltages together and it should equal 0.
Okay, if you take a loop and if you add the voltages together, it should equal to 0, right? Okay, so now that's basically what you select, right? So let's look at where that comes from. So what is the fundamental reason behind it, right? If let's say if I ask you to prove Kirchhoff's law, voltage law, how would you start?
Conservation of energy.
Okay, how would you go from, that's a good guess, how would you go from there to KVL?
Well, the energy provided by all the sources should sum up to all the energy that's dissipated by the...
Right, but you're adding voltage drops, aren't you? Not adding powers. Right? Okay, so let me make this statement here. You can assign a potential That means a voltage potential at each point in the circuit. So now I claim, if you start from this statement, you can prove KVL. By the way, my handwriting is actually not that bad. It's just my position, the way I'm writing it. It's actually better, slightly better than that. Okay, anyway. So, so if I start from that statement and I'll prove KVL, this could be a trick question. But first of all, do you agree with that statement? There's a slight caveat to that statement. What is that caveat? This statement is true technically, right? But it's not. There's a caveat. Okay, go ahead. Sorry, you're saying something.
Does that have the potential difference in your reference point?
There you go. That's the caveat, right? So what that means is this potential does not actually have to be unique. I can shift the potential at all points, up or down, but have to shift it the same way, so that differences remain same. Okay. But if I start from there, so that means if I see a circuit, I can say, okay, if I can pick one point to be ground, and I'll say, okay, that's 0 volts. And then I can assign a voltage at all points of the circuit. Okay, that statement is same as saying KVL. Okay, let's see why that is. Okay, so let's say I have some loop here, and I don't care what these things are. This can be batteries, this can be resistances, whatever. Okay, so let's take some 2 loops here. Okay, all right, so there are 3 let's put another one. This is not a good loop. Let's make a better loop. This one component, another component. Again, I don't care what these things are, and these things could be big circuits by themselves. All right, so all I found is these loops here. Okay, so let's start by assigning, let's say this is 0. It doesn't matter, it could be anything, right? So let's say, now give me your favorite number. Like 4, okay. What's here? 17. Here? 3. Okay. All right. So I'm saying these are this could, as you guys saw, this is completely random, right? I just pick some voltages. There are 4 different points which can have different voltages, and I gave those numbers. Now let's see the potential drops. Let's say this is one loop, right? Let's see the potential drops. What's the potential drop from this point to this point in this direction? In this direction, from left to right? Negative 13. In this direction? 17. That's nothing in this direction. Negative 4. Add these things up. Okay. Again, so in this loop, in this direction, what's the drop? Negative 17. In this direction? 14. In this direction? 3. Add those things up, 0. Right? See where it follows from? Okay, the fact that I can assign a potential at each point is the same as saying if you add up the potential drop across any loop, it's 0. That's where KVL comes from. Okay? So remember what that really, if you try to interpret the other way, so if you have a circuit, there is an electric field inside your components, right? And if you remember your physics, the potential drop between 2 points is the amount of work it takes to move a point charge from one point to another. Basically, you're moving against the electric field, right? Okay. So the potential drop between these 2 points is moving an electron or a point charge in this electric field from this point to this point. Okay. So let's say this is 0. The potential at that point would be the work it takes you to move that charge from here to here. But on the other hand, I can also take it from here to here. What KVL says is, no matter how you go, you should be able to do the same amount of work and get there. Okay, so again, if you're trying to compute electric, potential fields, you're basically integrating your electric fields. And what this theorem will say is no matter which line you take to integrate, the integral will always be the same. And that statement is same as saying if you integrate along a loop, it will be 0. Okay? And these are called conservative fields. For people who are more into math, if you do differential geometry, you'll come across this a lot. Especially if you take a function, you take a gradient of the function, that's a conservative field. Right? So curl of a gradient is 0. Remember that? That's what that is. That's basically a more mathy version of KVL. Okay? But for our purposes, all you need to so remember, where does KVL come from? It comes from the statement that we can give a potential at each point, or electric fields are conservative. That's what gives rise to KVL. Okay? Any questions so far? Okay. So if when I say any questions and you don't ask me questions, I'll assume that you understood everything. Okay? All right. So next. All right. Any guesses what comes next?
KCL.
KCL. There you go.
I know, right? I'm just.
And Kickoffs current law, or KCL. Again, can anybody remind me what that is?
All the currents entering or leaving a node equals 0.
Is 0, right? So if you have a node, let's say you can have another, again, boxes. These boxes could be, again, anything, right? They could be circuits by themselves. Okay. And then let's say current in this direction is I1, current in this direction is I2, current in this direction is I3. Okay, and then you have I1 plus I2 plus I3 equal to 0. That's KCL, right? And this doesn't have to be 3, it could be any number. The total current going into a point will always be 0. And can anybody give me where that comes from? Why is that true? Or if I ask you again, if you want to derive KCL, how would you do it?
I would probably use conservation of energy as an example again. Because,
Okay, so how would you use conservation of energy to do this?
well, or conservation of charge rather.
Conservation of charge. Okay, how would you use conservation of charge to do this?
Well, there should be no energy created or destroyed from the current going into
I
the
see.
node.
So, okay, here's the thing. So let's say, you can build up static charge, right? Right? I mean, we all have experience at static charges, right? So that means when you're building static charge is going into something and it's remaining there, right? So there is no loss of energy because energy is still stored over there, right? And then there's no loss of charge because charge is being stored over there. So then how would you derive KCL? Okay, so KCL is derived from actually stating that the charge is not being accumulated at any point in the circuit. Now, it's not saying it's impossible for that to happen. It is possible, but in the circuits we are analyzing, that's not happening. That's our assumption. It could happen. Static charge can build somewhere in your circuit, in which case you cannot apply KCL. Okay, and there are many cases where you cannot apply KCL because there is charge is accumulating inside something. But in our circuits, we'll assume charge is not accumulating. Okay, so basically at this point, you're saying charge is not accumulating at that point. That means all the current is nothing but charge per unit time, right? So if charge is not accumulating, the total charge entering any point is 0. That means the total current entering any point is 0. Okay, In reality, that's not necessarily true. KVL should always hold for electric fields and for electric potentials, right? But KCL need not hold even when there is charge being accumulated. But we are assuming charge will not accumulate. Okay, and then hence KCL. Okay, so for all our circuits, we'll use 3: Ohm's law, KVL, KCL, and that's pretty much it to solve resistive circuits. Right? Okay. Any questions so far?
What kind of like circuits with like cumulative charge? Like what kind of circuits?
Okay, so if you actually look at, in fact, even a capacitor, right? So if I have a capacitor, if I look at the entire thing, then there is net charge is 0. But if I look at just a plate, there is a net charge, right? So that means I can have a circuit which is just like this, a metal plate and a wire, and there can be current going in here. Right, so if you look at around this point, the sum net, because it's only one wire going in, the sum of all the currents going in there is not 0. That means there is just charge building up on this plate. It could happen, right? But if you look at the entire capacitor, there is a positive charge building here, negative charge building here, so the net charge will be 0. Okay, so especially if you're looking at some distributed systems, right? So, where there's a metal plate hanging there and you're feeding in charge, you cannot apply KCL at those things. But we will not be dealing with those in this class. Okay. And sometimes if you have like a complex, eddy currents going on, there could be charges building up in different places at different times and dissipating, building and dissipating. Again, KCL doesn't apply to every point on that metal plate. See what I'm saying? But again, we'll not be dealing with those complicated situations here. So it's always any point, total current going in is 0. Any questions? Okay. So next is, it's slightly, there are lots of options for where do you go next, but any guesses what we'll talk about next? There you go, very good. Thevenin equivalence, right? Right, so we're running through all the topics in circuits 1 at a very high speed, right? So usually that means when you go back, you should try and work out some problems, and I will release some homeworks for you to do that too. Okay, let's see. Okay, so Thevenin equivalent. Circuits. Before we talk about that, let's talk more general about modeling, right? For engineers, this is actually a very fundamental difference between how engineers approach problems and how scientists approach problems, right? So let's say if there's a box and it is doing something, all engineers care about is using that box to do something else, right? So that means I have to know how that box works. And in order to do that, all I need to know is a model for that box. If I know some mathematical equations on how output reacts to the input, I'm good as an engineer, because I can then use that knowledge to use that box somewhere else. But for a scientist, what's important is how that box works and what's inside. That's what they want to find out. They're not really concerned about using that box somewhere else. They want to know what's inside that box, right? For engineers, all we care about is using that box somewhere else, so just model it. I don't care what's inside, as long as whatever I model it has the same mathematical properties as that box, I'm good, right? So that's the whole, philosophy behind using equivalent circuits, right? I have a big complicated circuit, which is very difficult for me to deal with. I want to replace that with a simpler circuit, which behaves exactly the same way as that one. And then I'm good. As long as my simple circuit behaves exactly the way as the big one, if I replace that big one with the smaller circuit, all my calculations will be the same. And life is easier for me, right? So that's basically the philosophy behind modeling. And Thevenin theorem basically tells you, if you have a complicated circuit, how to model that with a simpler circuit. Okay, so whenever possible, if we can replace a complicated circuit with a simpler circuit, we will do so, because it will make our analysis easier, and everything will remain the same anyway. Okay, and we don't care what's inside the box. That's the thing. But we are all not purely scientists or purely engineers, right? We are somewhere in between. We want to use both of them. Anyway, so can anybody remind me what Thevenin equivalent circuit is? What Thevenin's theorem is? Let's go step by step. What's the first point of that statement? Let's stick to resistors.
So a circuit can be reduced into a source and a resistor.
There you go. Right. So slightly, if I want to add more, little bit more details, if you have any circuit which has current sources, voltage sources, and resistors, I can replace that with a very simple circuit which has only one source and one resistance. Right? And Thevenin's equivalent circuit means we can replace that with one voltage source and one resistance. Right? So okay, so that's for step number one. Is I have some box, right? And I don't know what's the configuration inside, but I know there are voltage sources, right? I know there are current sources, and I know there are resistances, like X number of them, Y number of them, and Z number of them, and I don't know how they're connected. All I ever have access to is 2 points where I can measure things. Okay. Then Thevenin equivalent circuit tells us, or theorem tells us, that I can replace that box with a box which has this inside it. That's it. Now there could be like a million of these guys, a billion of these guys, it doesn't matter. I can always replace that with this. Right? As long as, if I'm only measuring things at these two terminals, these two boxes will always, I'll always measure the same stuff. If I measure the voltage or resistances, I will always measure the same thing across these two. Okay, so I'm replacing this entire circuit by this simple circuit. Okay, so we call this V Thevenin and R Thevenin. So that's step one. That means step one says we can actually replace it with this simple circuit. Okay, and the theorem goes on more, tells us more. It also tells us how to calculate these values, right? Or how to measure those values. How would you do that?
For the resistance, the Thevenin resistance, you add every resistance in series or parallel.
Right, but you don't know how they're connected.
Don't you short circuit all the sources?
Okay, yeah, so you just go into the box and switch off all the power supplies. Right, so switching off the power supplies means most often shorting them. Right, if there are current sources, you open it. Right, so that's how you switch off a current source. You open circuit. Right, so go into the box, switch off all the batteries, or if current sources, disconnect them. By the way, the current sources are real; they're not mythical, and we will construct a few of them in our classes. In fact, when you do ICs, you'll only deal with current sources. Okay, but we'll talk about that later. Okay, so you go into the box, switch off all the voltage batteries, you switch off, disconnect all the current sources, and then what you do?
And then you add up all the resistors.
Or you take a multimeter, measure the resistance. Right? Again, you don't know how they're connected, so you don't know how to add things up or parallel. Sometimes they may not be in series or parallel, right? So you have to do some more complicated calculations if you have to do calculations, or if you have a multimeter, just measure the resistance, right? Or if you have to calculate, then sometimes not all configurations are series or parallel. So you have to do some more complicated calculations to figure that out, right? So how are you doing it? Figure that out. So switch off all the power supplies, measure the resistance or calculate the resistance, and that's R Thevenin. Okay, how do you figure out what V Thevenin is?
Measure the voltage of the terminals.
That's it. Don't connect anything between these two terminals. Measure the voltage. Okay, and that's V Thevenin. That's it. Right. So now, whatever you connect here, let's say you connect some resistance. The current going through that resistor will be exactly the same as the current going through the resistor if you connect the same resistor here. Okay. So as an engineer, what you want to know is, okay, if I connect something here, how much current is going through? Instead of analyzing this circuit, you can just analyze this circuit and figure out what that current is. Right? This is easier than this. That's the use of that theorem. That's why you use it. Okay. All right. Any questions so far? Again, any guesses what's next? We just did Thevenin equivalent circuit.
No.
Norton theorem. There you go.
Can you just do a source transformation of this one?
Yeah, that's what I'm gonna do. Okay. So now Norton's theorem. First, let's state Norton's theorem, and then we'll do the source transformation, right? Norton's theorem. Okay. So far, what we had is, this is another advantage of using notes, that if I erase if on the board if I erase something, I cannot go back, but on notes I can always go back. Right. Okay. So far we had a box. We replaced that box with this simple box. Okay. But we don't have to replace it with this sort of a box. We can replace with in this box we have a voltage source, right? But we can also replace it with another simple circuit which has a current source in it. And that's what Norton theorem is. Okay. All right. So again, let's start. Let's say we have this box to start with. Let's see. Okay. So we have that box to start with. And then we want to replace it with another simple box, right? And Norton's theorem says that we can replace it with something which looks like this. A current source, let's say I Thevenin, with a resistance in parallel R Thevenin. Okay. So instead of a box which looks like that, you can also use a box which looks like this, which will behave exactly the same as this box. Okay. Now, how would you calculate this I Thevenin? Short what? These two terminals? Yeah, just short those two terminals, measure how much current is going through them. Right? But in general, in a circuit, if that's an output of some circuit, you probably don't want to short it, right? In which case, you just want to do some calculations, right? But even if you want to do calculations, you short that and then measure the current in calculations. Right? So you short it, measure how much current is going through. That's I Thevenin. How would you measure this R Thevenin?
Disconnect all voltage sources and unplug all the current sources.
And measure the resistance. Okay, the same exact way you do in case of this.
What's the benefit of using Norton's Theorem?
Okay, sometimes that's a very good question. Right? So sometimes there are some sources which are better modeled as voltage sources. They're exactly the same mathematically, right? So mathematically there's no difference. Sometimes some sources are better modeled as current sources, some are better modeled as voltage sources. And here's why. So if we have 3 minutes, I think this is where we can discuss this point, and we'll continue this in the next class. So if I want you to define a voltage source, how would you define a voltage source? This class ends at 8:50. How would you define a voltage source?
Can you repeat that?
How would you define a voltage source?
A certain amount of current going through a certain amount of resistance.
A voltage source, like a battery. Like how if I'm saying, okay, I take a battery and they say this is acting like a voltage source. How would you define it? This is a slightly vague question. So let me say what I mean. You define it like this: no matter how much current you draw from it, the voltage difference between its terminals will always be V. Okay. So that's a voltage source. That means it will supply the voltage of V no matter what you connect to it. Okay. So what's the definition of a current source?
You always apply the same amount of current no matter what you add to it.
Exactly. Right. Okay. Now, for an ideal voltage source, what should be let's say if this box is acting like a voltage source, what should be the output resistance? This is R Thevenin for an ideal voltage source. What should be R Thevenin? 0, right? If it is 0, no matter how much current you're drawing from that, the voltage difference between these 2 points will always be same. For an ideal current source, what should be the output resistance? should be infinite, right? So it means if this is open, then no matter what you connect here, you'll always get the same current. Okay, so that's the difference between an ideal current source and it's the difference of voltage source and a current source, right? Now sometimes some devices have very high output impedance. Very high output impedance, in which case you would want to model it as a current source.
Oh, so you judge the Thevenin and Norton based off of the resistance that's coming out of the box, and that's how you, okay.
And sometimes output resistance is very small, so you want to model it as a voltage source.
That makes sense.
Okay.
So what would you consider like high impedance?
It really depends on what you're connecting next to it. So it's relative to that. And when we will do like amplifier models, and we'll talk about that a lot. So we'll stop here. We'll continue here next time.